Le Chatelier's principle. In chemistry, many reactions can happen in the forward direction as well as the reverse direction. A system at equilibrium is a system where the reactants transform into products at the same rate as the products turn into reactants. A good example that illustrates this concept is a bottle of pop. The bubbles are carbon dioxide gas. In the bottle, there are bubbles in aqueous form, so they are dissolved in water, and there's also some gaseous carbon dioxide that fills the remaining part of the bottle, not filled with liquid. When we open the bottle, the pressure of the system decreases, and the system reacts by quickly converting aqueous carbon dioxide into gaseous carbon dioxide, which forms new bubbles and helps increase the pressure. The system's response to this change in pressure aims to re-establish an equilibrium, and is an excellent demonstration of Le Chatelier's principle. By definition, Le Chatelier's principle says that when a system at equilibrium is disrupted or modified, the system will adapt and move towards a new equilibrium to try to offset the effect of the disruption. In chemical synthesis, we exploit this concept to maximize the yield of reactions. Imagine Le Chatelier's principle like a scale. The addition of products or reactants to one side of the scale will throw off the equilibrium. By adding X amount of reactants, we are displacing the equilibrium to the right, in the forwards direction, and an amount X of products will be formed. On the contrary, if we add products to the system, the reverse reaction will take place and the products will be reconverted into reactants in order for the system to find a new equilibrium. By eliminating carbon dioxide as soon as we produce it, we are reducing the quantity of products that are being formed. The equilibrium becomes unbalanced. In order to re-establish an equilibrium, the reactant, calcium carbonate, will dissociate more quickly into products until the amount of reactants and products become proportional again. It is at this moment that a new equilibrium is attained. In this case, we are therefore favoring the forward reaction, the conversion of reactants into products. Note that for certain reactions where we are in the presence of liquids and solids, Le Chatelier's principle that says that the more reactants we have, the more products we will have, does not always apply. For example, a system consisting of ice and water at 0 degrees Celsius has both ice and water coexisting in equilibrium. If we add ice to the system, it would not make more water be formed, and if we added more water would not be converted into ice. Without the gain or loss of heat, the system stays at a fixed composition. The Le Chatelier rules that would apply in this situation would be pressure, concentration, and temperature variations. When talking about temperature, we have to consider Van 't Hoff's law. This law says that an increase in temperature of a system at equilibrium will cause a displacement of the equilibrium in the direction of the endothermic reaction. In other words, because a reaction needs heat to happen in the forward direction, if we add heat to the system, we would be unbalancing the equilibrium by stimulating the formation of additional products. However, if we added heat to an exothermic reaction, we would be favoring the reverse reaction for the system to find a new equilibrium. An easy way to think of it is to imagine heat as a reactant for endothermic reactions and a product for exothermic reactions, and then treat the increase or decrease in temperature as an increase or decrease in reactants or products, just as you would with any other question. In this situation in particular, the conversion of oxygen in its aqueous form into its gaseous form, delta H, is negative. This means that the reaction is exothermic, so heat is released, and we can visualize it by placing heat on the product side of the equation. If temperature is increased, the reaction becomes unbalanced. There is too much heat on the product side, so the reverse reaction will be favored, which is an endothermic reaction, to create more reactants and re-establish the equilibrium.